Hello everyone and welcome to a new tutorial. And in today's video, as you can see, we have a tensile test. As some of you might know, we already did a tensile test before. And in today's video, we have this tensile test made from shell element, and we try to convert it to a solid element. Okay, so this file can be found online from the DYNA example website, which is here, and the link will be given in the description. But I advise you to go back to my tutorial where I did the tensile test. From there you can learn a lot of things. And in today's video, I will try to cover things that I have not covered in that video. So here you can see the results of that file. Okay, this is the result. I run the file from the website without any changes. So as I mentioned before, I have this shell element and I want to make it a solid element. Okay, so I copy the file, new folder, solid, then I paste it, then I modify this file. You have some warnings here, is okay, you can just ignore them. So first I want to make the solid the same thickness as the shell element. So I need to find out what is the thickness of this shell. Section shell and is 2.67 millimeters. So I copied that value already. I go to mesh, element generation, and then solid, and by face drag, click by part, click the shell part, and then this is the thickness and the direction is set. And how many segments, meaning how many layers I want to have here. Let's say I want to have 3 layers. If you look from the right side, you have here 3 layers. You can increase or decrease, up to you, but here I'm just trying to use, I will just use 3 layers. Okay, so now I want to find out whether my thickness is the same or not as the shell element. I mean, I want to find whether this solid is the same as have the same thickness or not. So I want to display the thickness of the shell. Appear, thickness, and mesh. And you can see here the thickness is a bit going down. I will show you from the side. And you see here the red 2 lines represent the shell and the blue lines represent the solid part. Okay, so I can actually shift it up and down and you can see that they are exactly the same. Or you can do another thing from here. You go to section, shell, and this one, the reference surface, you put it equal to 1, then accept. Then you can see now this the solid and the shell are actually uh, overlapping with each other, meaning they have the same thickness. And interestingly, you can see here the shell or the I will hide the solid for the time being. You can see that this is going up, but here this one is going down, meaning the normal of the shell have been changed from this portion to this portion. Okay, so what I can do here, can just hide the thickness and then go to go to element editing and normal, and you can see as expected here the normal is going one direction and here the normal is going the other direction. Show normal by part, you can see this is going down and this is going up. So I can just reverse the normal and then by area, and now I click by part, should click by element, and now all the normals are going the same direction. Okay, now if I go back to appearance and show the thickness of the shell, I will have like this. Then I show my solid element that I did before. You can see they have the same thickness. Okay, I can do the same thing, go to the keyword, go to the shell, and then here instead of 1 I put -1. So now you can see they are overlapping, and you can see they have the same thickness, which is 2.67. Okay, but anyway I don't want this shell, so I can just delete it. Here I show the shell part, element editing, then delete by part. Okay, now it's deleted. Bye bye. Now I go to here and I show the solid element that I want to model. And then what I can do now, go to model, and then sorry, before I go there, I go to element tools, move copy, and then by part, here I click part list. Yes, I put number 1, apply. Okay, now this one become red. Why I'm doing this? Because of two things. First, the material properties is already defined and linked to part number 1. And if part number 1 is defined in any of part set, then that problem will be already resolved. It will not give you any problems. Okay, so now I go to model. I need to define the solid section. This shell section, I don't want it anymore, so delete. Then I go show all, go down solid, the new solid, and the default element formulation is fine. Go to model, part. Now I need to delete this one. This is actually the remnant from the blue part that I made it. Okay, because if you paid focus, I made the blue part, then I converted to the red part, which is part number 1. So the blue part number 2 is still there, but I need to delete it. Part here, instead of shell, of course we don't have shell, we have solid. Then accept. Okay, and then I need to, last but not least, you always remember, if you remesh or you played with the mesh, remember to update your set of nodes and your boundary conditions. So here you can see this side is fixed, okay, but only the lower nodes are fixed, because in the original file we don't have these 2 more layers. So I go to create, and then you can see fix in all directions and in all rotations. So I click by element, propagate, then I click by edge, and I right select this one. This by doing this, I'm only selecting this portion of the nodes. These ones, uh, they are already fixed, so I don't need to fix them again. I don't need to do double constraint. And then I go to the other side here, the same story. If I go to show, the same story here. Okay, I go to create, pick the nodes, and then the load curve is load number 1. Here, load curve is load number 1. I read to show it, and you can see this is actually the displacement curve. Okay, the displacement is going up with the time, and it's a straight line, meaning the velocity is constant. So this curve is velocity curve. So VAD, this one should be equal to D, because it's a displacement curve. The curve just now is number 1, and degree of freedom is 1. This is vector ID, no need, because we are just going straight in the X direction. Select the nodes. Okay, the same trick like we did over there. Select by element, propagate, then by edge I unselect the lower nodes, and then apply. Okay, now I think everything is done. I save, already saved twice also. Before I close, I just want to check everything is okay. Model check, keyword check. Okay, you have one error in the database. If you open here, you have history shell. Okay, why? Because we deleted the shell from before. So this one is actually we are requesting the history of shells that are no more there. So I need to delete those guys. Database history shell, then apply. Okay, now I go again, model check. Okay, it's still not updated. Okay, I recheck. Now I don't have any error. Okay, these warnings is okay. You don't need to worry about them. As long as they are not errors, then your model will run without any error termination. So this is done. Now browse. Okay, I maximize my resources so it doesn't take time. Okay, just wait. It will just take a couple of minutes. Yeah, 2 minutes. And now the element have been deleted, meaning the rupture has happened in the specimen. And it's gone. Okay, now I open the results. Okay, this is the model just now, and this is the original result of the shell element, and this is the result of the solid element. Okay, and you can see it's almost identical, if not exactly identical. You can see this one from shell element and this one of solid element. Okay, the rupture happened in two places. Oh, here also it happens in two places. Okay, I stop this too. Stop. Okay, now the shell element, I go to history, not history. I go to SQ options. This is the previous file or the original file. I go to nodal forces and load everything, and then click all, and then the X-force plot, and now I have this result. Okay, what I'm doing here, I'm clicking on the nodal forces at one side. Okay, remember this side I have 1 2 3 4 5 6. Okay, these are the nodes, or I'm plotting the forces from those nodes. Okay, so each force have some forces. So if I go here and I click on operate and sum the curves, apply. So if you see, this is actually the force from the nodes. Okay, so if you divide by the cross-sectional area, then you will get the stress, and you can compare to the experimental result. Here I do the same thing. SQ option, then nodal forces, load. I have the same thing. Click on all X forces, then apply. Okay, and then I do the same thing, operate, and then sum curve, apply. Okay, put here and I put here. Okay, this is from the shell element, and this one is from the solid elements. Okay, you see we have the same pattern, but we don't have the same values. Okay, here from 0 until 10 it goes down a bit, then the maximum is around 25. Okay, but here it has the same pattern, but the values are not the same. Why? And I will tell you why. because here we are extracting only the forces of few points, which is 1, 2, 3, 4, 5, 6, 7. Okay, 7, the forces of 7 nodes. But here in the solid element or in the solid model, we have more than 6 nodes in one end. Okay, so that's why we have the difference in the result. And where is my model? Here. Okay, need to close. No, where is that guy? Nodal force group. Here, because I have not updated the node number 2. Okay, you can see this nodal force group is the forces, is the group of nodes that which will appear here. Okay, these nodes, but I have not updated them. So if I want more nodes to be there, I need to set nodes, and this 7 nodes, I click on modify, sorry, show, then modify. Okay, you see that I'm having only the lower nodes here. So if I update all of them, then I should get the same result. So modify by element, then propagate, then apply, and I save. Okay, the solid element result, I can close it. I save already. So now I want to rerun. Okay, we just open the results now. We don't need actually the full results, because the maximum force occurs before the rupture. So I go to history, sorry, not history, I go to SK option. So I just close. I go to nodal forces, load. You can see I have more nodes now. Select on all X, and then plot. I have so many curves, operate, and then sum the curves and apply. Then you see the same value as the curve from this shell model. If you sum, you will get the same. Okay, so this vibration happens because the specimen already ruptured. That's why you have this instability. Okay, but here I want to cover one more thing. You can see here, after the rupture, the element, actually this part, go through this portion, which is not nice. So what I'm trying to do now, I will try to avoid that thing, because even in the solid element you can see the same thing. So actually I don't want that to happen. So how to do that? I need to define the contact. But how do I define it? I will define it using node to surface. Okay, so here define nodes by part, and then here all nodes apply, and then I go to keyword, show all, go up, and contact automatic nodes to surface. New, I say here self contact, and then the slave is node, so 4, and the master, I want it to be segment, so it's 0, but I don't have any segment here. So I define by new entity, and then click by part. Here all segment, then apply. Okay, then I don't have any friction or anything, no need for that. for the time being. Okay, please don't hang on me. Okay, and save. Come on, I want to save. Okay, save. And then I rerun again. Okay, what I'm doing here, you see these black things are the segment set, and this node, the green one are the node set. So I'm defining the contact between both of them. Okay, you can see the time increase from 2 to 3 minutes. This is because I defined the contact. And depending on the contact definition and the contact type, your simulation time might increase. But this is a fairly or a very small model, so it won't take a very long time. Okay, close. Now I open the, sorry, not here. I open the results. Okay, here you can see, okay, breaks and it hits the other side and it bounces back. Okay, so it doesn't go through the left part. Okay, that's everything for the solid model. Okay, I close this one also, and here I have the shell model. Okay, one last thing to discuss about this model is how to get the result of the forces. As I mentioned before, you can go through SQ option nodal forces, and these nodes you need to define it, of course. When you click the force of each node, then you sum them up, and then you get the force, you divide by the area, and you can compare with the stress curve that you get from the experimental results. There is another way, which is section force. Okay, this section force, if you load it, you have only one section, and then you plot. You can see we have the same exact result. Okay, it goes up until 15, goes down a bit, and the maximum happens at almost 25. Okay, and how to define this one? This is, you can refer to the file, the original file. You define in the database here, you define database cross-section plane, and in the ASCII option, you need to define one more output as well. Okay, here, this is the original file from the website. You see database, you need to define cross-section plane, and here is the a section which cuts the specimen in the middle. Okay, can I draw this? Okay, you can see this is the section. Okay, I don't know why they make it rotated in that way, but anyway, this is the section that cut through this specimen. And if you do this keyword, and in the ASCII options also you ask for the output, then you will get this. You will be able to get the result from this seg force. Okay, here in the database option, you need to define this seg force. Okay, so I think I just leave this one open, and I will modify it again. And this one I will make shell element, but I will try to make it variable thickness. So I copy here, paste here. This one gonna be a fast one. we're gonna maintain it as shell element, but we just going to play with the thickness. Okay, again, just ignore this one. Okay, so you have 1 2 3 4 5 5 5 lines. Okay, so each one of these lines we will define a section to it. So first I want to correct or modify the normal. So reverse the normal by area here and done. And then I want to make them into different parts. I go to move, copy. This will remain as part 1, so no need, or I just make it part number 1 2 3 4 5, make it part number 5, and I unselect this, unselect this. Okay, now the second layer here, and this one will be number 4, and here is number 3. Oh, I made a mistake, I think. 2 3 4, not sure why 3 and 4 has the same color, but anyway, let's just proceed. And then the last but not least will be part number 2. Let's unselect this guy, select this one. Okay, not sure why this color is not working fine, but just want to check here. Part, I have 5 part 1 2 3 4. Okay, the material, of course I don't want to play with the material, all of them will be number 1. Okay. Now I want to define the thickness. Okay, so this one, let's say it's from 1.5, and then it will be 2.5 and 2.5. Okay, and then I click on appear, click on thickness. Okay, this is the part number 1, which I just changed the thickness. Okay, so maybe it should be the other way around. I will try to assign this section 1 to part number 5. Okay, and it's the same way. I think it should be like this. And here is 1.5. And see how the thickness is changing. Okay, anyway, I think just like before is working fine, or just click on right. The thickness here is not the same, so I think like before it was correct, and here is 2.5. Okay, now I define the second thickness, make it 2.5, here 3.5, 3.5. And then in the middle thickness, let's say it is constant. Then the fourth thickness, it's going down. So from 3.5 to 2.5, and then the last one is from 2.5 until 1.5. Here also 1.5. Okay, now let's assign these sections and see what happened to our model. This is 2, coming fat. This is 3. Okay, more fat. This is 4, and this is 5. And you can see here from the front view, this is the guy. Sorry. And this is how it thing become. I click on back. Okay, so this is how you make the variable thickness. Okay, this is actually a shell, and yeah, if I click here, you can see it's shell, but here you have variable thickness. Of course, if you want more smooth, you need to have more elements and more of these lines. Okay, so I think that's all. You just try to run this and see if it's work fine or it gives error or how. Okay, one more thing to mention here, what we did here, the thickness that we played with, T1, T2, T3, T4, depends on the orientation of the elements. Like this is, we have 4 points. This is T1, T2, T3, T4. So in this case, it was 1.5, 1.5 here and here, and here is 2.5, 2.5. Sometimes if the orientation is different, it might be 1.5 here and 1.5 here. Here and here is 2.5. So it depends on the elements and how they are constructed. And this error, okay, there is a part that I have forgot to define the thickness. I think I was too fast. Okay, here, 2. Okay, sorry. The material thickness is defined, the material was not defined. Okay, now I save, I rerun this. Okay, you can see fewer elements have failed, meaning in this one I suspect it failed only in one side. It did not break in 2 parts, in 2 portions. I think the rupture happened only in 1 point. And yes, as expected, only here. Here there is no rupture. Okay, so this is how you make it different thickness. And we go to color. If you don't like this multiple color, you can just make it all the same color. Click home. Okay, so now they look like one part. Appear thickness again. So here you can see how it fails. Okay, so that's all for this tutorial. I hope you learned something, and don't forget to like and subscribe. Thank you, and see you in the next tutorial.